Hello everyone and welcome back to Math 110, Introduction to Number Theory. In this video we'll discuss congruence modulo n, which is commonly known as modular arithmetic. And as a word note, modular and modulus are referring to a Latin word meaning a small measure, which isn't in common use these days, though in engineering there are things like Young's modulus and so on. The invention of congruence is by Carl Friedrich Gauss, the mathematician from the late 1700s, early 1800s, who was very, very productive and came up with quite a lot of things. In fact, so MSRI, the Mathematical Sciences Research Institute up the hill from Berkeley, is next door to the Space Science Laboratory, and they're both on the same street. And when they were built, they had to decide on what they were going to call that road. And the only thing that they could agree on was Gauss Way. In fact, when MSRI proposed Gauss as being the person who would be named after, the space science people were like, oh, Gauss was a mathematician too? Just because he had done so much physics. Anyway, so this all comes originally from a book called Arithmetical Investigations, though in Latin, written when Gauss was around 20. And in it, he created this idea of congruence of numbers, which helped streamline a lot of number theory that had come before. And so we're going to now see how Gauss did things. And so just generally speaking, congruence is a systematic and also very convenient way to reason about remainders after division. So let's get into the definition. Let's say that we have three numbers, a, b, and n in the integers, and let's say that n divides the difference of a and b. If this is the case, then we say that a is congruent to b modulo n, and also sometimes we say a is congruent to b mod n, just for short. And there are two notations that are in common use. There's the traditional notation, which is a is congruent to b mod n, which is a reprise of the words in the definition. Or there's a is congruent mod n to b, which is also pronounced a is congruent to b mod n. So one thing to note is that this mod n in parentheses at the end is not an operator or anything like that. It's just part of this congruence notation. So if you have a CS background, then you might be thinking that we're computing something here, but it's just saying that these three numbers stand in this relationship of congruence mod n. Yeah, so that's something that confused me when I first was learning about this. So we're going to use the second notation throughout the lecture. So let's look at a couple of basic examples. So one thing is, if we have an odd number, so 2k plus 1, it's congruent to 1 modulo 2. And that is because, well, let's take 2k plus 1 minus 1. That is 2k. And 2 certainly divides 2k. So we can write that 2k plus 1 is congruent to 1 mod 2. Here's another example. So 8 squared is congruent to 5 squared mod 3. And one way that we can see this is, short of actually just taking 64, 20, and 25, taking their difference and seeing that it's a multiple of 3, is that, well, the difference between squares can be written as a product of their sum and their difference. And their difference, 8 minus 5, is 3. So 8 squared minus 5 squared is a multiple of 3. And so we say 8 squared is congruent to 5 squared mod 3. So those were two examples. So here are some lemmas that give us some characterizations of congruence that will help us get some more understanding of how all this is supposed to work. So let's say a, b, and n are integers like before. And then a is congruent to b mod n if and only if there exists some integer k such that a equals b plus kn. So this is just rewriting the definition of congruence. So instead of saying that kn, so n divides a minus b is the same as saying that, kn equals a minus b, and then we add kn to both sides. So anyway, just to quickly go through this easy proof. So if a is congruent to b mod n, that's equivalent to n dividing a minus b, which is equivalent so that's by definition, and then this is by definition too, that there exists some integer k such that kn equals a minus b. And then we add b to both sides, rearrange, and we get what we wanted to show. So the idea with congruence is that congruent modulo n means like equal up to a multiple of n. So throwing away multiples of n, the things are equal. And actually, modulo shows up in some common speech, at least among mathematicians, scientists, and engineers, where they say that something is true mod something else. I mean, when you throw away that detail, then the things are the same. Okay, this is a useful lemma, and it's a way to sort of normalize different congruence equations. So if we have two integers, a and n, where n is positive, then a is congruent mod n to a mod n, or like the remainder of a divided by n. And this is easy with the lemma, because in the definition of this a%n, or of the remainder, we know that a is equal to the floor division of a by n times n plus the remainder of a divided by n. And so, having this be k in the previous lemma, then we see that a is congruent to a%n mod n. Or using how I've been saying it before, a is congruent to a mod n, which is a little ridiculous sounding. But like this one's the operation, and the other thing is just this relationship. You might have heard about clock arithmetic before, because it's a good popularization of mathematics and number theory. So let's see what that looks modulo 5. So what I've written here are the number line out to a certain point, and each of these colored dots is representing a different, I guess, what's known as a congruence class. So 0 is congruent to 5 mod 5, and also it's congruent to 10 mod 5, and minus 10 mod 5, and 15 mod 5. So all the multiples of 5 are all congruent mod 5. Similarly, like 1 is congruent to 6 mod 5, because 6 minus 1 is 5, which is a multiple of 5. 1 is also congruent to 11, because 11 minus 1 is 10, which is a multiple of 5, and so on. So we've got these 5 colored dots randomly chosen by me, and if we look at the pattern, it's just that every 5 dots has the same color. So one way to represent when you have this periodicity is to take the number line and wrap it around a circle, so that every 5 it ends up being at the same angle around the circle. So for the gray dots, that's like 0, 5, 10, and all the multiples of 5, then 1, 6, and 11, and so on for orange, and so on. So it's like a clock in that as the hand goes around, once it goes around in a full circle, we end up back where we started. So anyway, so if we keep adding 1 to a number, eventually we'll get something that is the same mod 5, and that's after exactly 5 steps. Okay, one concept that's related to the previous lemma about a%n is the residue of a number modulo n. So if we have 3 numbers, a, r, and n, where n is positive, and if a is congruent to r mod n, and if r is also a remainder, like in the division algorithm, then we say that r is a least residue of a modulo n. Least I'm putting in parentheses because sometimes that's people say least residue instead of just residue, but whenever I say residue, I'm going to mean this number in this range. So the last lemma says that when we take the remainder after division, then that remainder is the residue of A modulo n. So residues do exist. And also, this is the justification for why I've been saying A mod n for the remainder until now, or up to now. So one neat thing about remainders is that they give us a way to tell whether or not two numbers are equivalent. They give us a way to tell us whether two numbers are not equivalent. Because so far we only have a way to say that they are equivalent. And here's the idea that if we have a residue of a number modulo n, then that number just is the remainder. So one thing that this means is that if A mod n is congruent mod n to B mod n, then in fact A mod n equals B mod n. This is actually an equivalence, but it's the forward direction that's the surprising one, because whenever two things are equal, they are also definitely congruent. So that's an exercise in the uniqueness of division. Congruence is special because it's like equality. And in mathematics, things that are like equality are called equivalence relations. And equivalence relations satisfy three properties, just like equality: reflexivity, symmetry, and transitivity. So reflexivity is that things are equivalent to themselves. Symmetry is that something is equivalent to something else, means that something else is equivalent to the something. And transitivity is that you can chain equivalences. So let's see why congruence is an equivalence relation. So reflexivity. So if you have an integer, then that integer is congruent to itself mod n. And so this is easy to check. A congruent to A mod n is by definition that n divides A minus A, but A minus A is 0, and so it's 0 times n. And so the definition of divisibility sort of obviously holds with k equals 0. Symmetry. So let's say we have two numbers where that are congruent mod n. Then we want to show that they're congruent in the reverse way. So let's suppose that they are congruent. And then, by definition, n divides A minus B. And by definition of divisibility, there exists some integer k such that the A minus B equals k times n. And then, if we multiply both sides by minus 1, we get B minus A equals minus k times n. And then by definition of divisibility, n divides B minus A, and thus B is congruent to n, or B is congruent to A mod n. Okay, so that's symmetry. And now transitivity, it's the one, like the previous two are, I think any mathematician would probably call these trivial because you just expand out the definitions and then you can, by piecing the definitions together, you can see that it's true. And so transitivity, it's a little less trivial. So if we have three numbers, A, B, and C, where A is congruent to B mod n and B is congruent to C mod n, then the A is congruent to C mod n. So for this proof, we suppose that these two congruences hold. And then let's let k and h be integers such that A minus B is k times n and B minus C is h times n, using the definition of congruence mod n. Then we add the two equations together to get this, and then rearrange things. The b's cancel out. That's the nice thing here. So we get A minus C is equal to k plus h times n. So n divides A minus C, and so A is congruent to C mod n. So great, it's an equivalence relation, so it behaves like equality. The other important thing about congruence is that it respects arithmetic, and this is what makes it be called modular arithmetic. And respecting means that whenever you have an addition or a multiplication, then you can replace things with congruent things to get another thing that is congruent. And then this is what will let us do a lot of manipulations. So these are important theorems, in addition to the previous three about being an equivalence relation. So, okay, so let's say that we have four integers, a, b, a prime, and b prime, where a is congruent to a prime and b is congruent to b prime all mod n. Then a plus b is congruent to a prime plus b prime mod n. That is what we want to show. So let's suppose that the two congruences hold, and then we want to show that the conclusion congruence holds. Like usual, let's let k and h be integers that demonstrate the divisibility that's underlying these definitions. So a congruent to a prime mod n means that there exists a k where a minus a prime is kn. And also b congruent to b prime mod n means that there's this h such that b minus b prime is hn. Now what we do is we add these two equations together like so, and then rearrange. It's very much like transitivity here. So then we have a plus b minus a prime plus b prime in parentheses is equal to k plus hn. And so n divides this difference, and so therefore we get the congruence that we wanted, that a plus b is congruent to a prime plus b prime mod n. Okay, so multiplication. This one is much more, well, okay, it's slightly more involved. It's not bad, and it's something you could figure out yourself. It's not just like, I guess, adding two equations together. Okay, so multiplication. Like before, we have these assumptions about congruences of a prime and a and b prime and b. And what we want to show is that ab is congruent to a prime b prime mod n. Okay, so we suppose that we have these congruences, and just like before, we say k and h are the integers so that these two equations hold. And now here's what we notice. So we want to see that this difference is divisible by n. So let's start with that difference right here, aab minus a prime b prime. And then these two equations, we can solve for a prime and b prime and substitute it in. So now we have ab minus a minus kn for a prime and b minus hn for b prime. Then we expand it all out, and then the ab's cancel out, which is nice, because the remaining terms are all divisible by n, which we can so we can factor that n out. And since we've shown now, just symbolically, that this difference of products is something times n, then in fact that difference is a multiple of n, and so ab is congruent to a prime b prime mod n. Okay, so we now have that congruence mod n is an equivalence relation, and we also have that it respects addition and multiplication. What about subtraction? So again, with the same equivalences, why is it that a minus b is congruent to a prime minus b prime mod n? So I want to show you how we can just use what we've already shown without digging into any of the properties of divisibility or anything like that, and show that this does hold. So one thing that's useful is this claim, which we'll see why we want it in a bit. And that is that minus 1 times b is congruent to minus 1 times b prime mod n. So by reflexivity, so this is the reflexivity law, minus 1 is congruent to minus 1 mod n. And we have this assumption that b is congruent to b prime mod n. And so by the multiplication law, that we proved, then minus 1 times b is congruent to minus 1 times b prime. Okay, so now let's show this congruence directly. So we have a minus b is equal, of course, to a plus negative 1 times b. And then, using the multiplication law, or the addition law, we have, well, first of all, by assumption, a is congruent to a prime. And by our claim, minus 1 times b is congruent to minus 1 times b prime. So by addition, then a plus minus 1b is congruent to a prime plus minus 1b prime mod n. And then that's equal to a prime minus b prime. So that is what we wanted to show, that a minus b is congruent mod n to a prime minus b prime. So in general, what all these different properties give us is that if we have an expression that involves only addition, subtraction, and multiplication, then we can replace any sub-expression of it modulo n. So if some sub-expression is congruent to some other expression mod n, we can just replace it and get something that is equivalent mod n. So let's look at some examples now. So this one is a classic one, and it's actually a pretty good way of testing divisibility by 9. And it's that every natural number is congruent to the sum of its digits in base 10, modulo 9. So for example, 18, we can see that's congruent to, so 18 is 8 plus 1 mod 9 according to this, and 8 plus 1 is 9, which is a multiple of 9, so 18 is a multiple of 9, though it's also 2 times 9. Or how about 1, 2, 3, 4, 5, 6, 7, 8, 9? According to this theorem, 9 ones is the sum of the 9 digits, which is equal to 9, which is 0 mod 9. So therefore, this number is a multiple of 9. And we didn't even have to find any factors or anything like that. Okay, so how do we prove this? And the main observation is that 10 is congruent to 1 mod 9, because, of course, 9 divides 10 minus 1. 9 divides 9. So, what we can show is that for every natural number, n, 10 to the power of n, which is defined to be the product of 10 n times, is congruent mod 9 to 1 times 1 times 1 n times, because we're using the multiplication law repeatedly, replacing each thing in this expression with something that it is congruent to mod 9. And any number of 1s multiplied by itself is 1. So 10 to the n is congruent mod 9 to 1. And as an exercise, you should prove this properly with induction, induction on n. Anyway, so let's now suppose that we have a natural number n, and we have a0 through ak being its digits. So that's to say that n can be written as ak times 10 to the k plus ak minus 1 times 10 to the k minus 1 plus dot 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 plus a2 10 to the 2 plus a1 times 10 plus a0. So a0 is the ones digit, a1 is the tens, a2 is the hundreds, and so on. So n is congruent mod 9 to ak times 1, because 10 to the k is congruent to 1, plus ak minus 1 times 1, because 10 to the other power is 1, and replacing all those powers of 10 with 1, we get this expression. And then, well, we're just multiplying by 1, so we can simplify that and get the sum of all the digits. So that's that. Very quick. So an example of an application is 1, 2, 3, 4, 5, 6, a multiple of 9. So according to that theorem, to find whether it's a multiple of 9, we just want to know, is it 0 mod 9? And so mod 9, according to the theorem, is the sum of the digits. This number is the sum of its digits, mod 9. And I was feeling a little lazy, and I didn't want to actually add all the digits together. So I used the Gauss trick, which is that 1 plus 6 is 7, 2 plus 5 is 7, and 3 plus 4 is 7. So there are 3 7s here, so it's 3 times 7. And still I was feeling a little lazy, and I thought, well, this is 3 times 6 plus 3 times 1. And 3 times 6 is 0 mod 9, because, well, 6 is 2 times 3. And so using the addition law, this quantity is congruent to 3 mod 9. And 3 is not 0. And also, 0 is less than or equal to 3 is less than 9, so it's a residue. So we know that this number can't possibly be 0 mod 9. Yeah, so it's not a multiple of 9. Right. So I guess another thing we could have done is been like, well, this is 21, and then using the theorem again, it's 2 plus 1, which is 3. So anyway, it's 3 mod 9 either way. Here's another example. Is the same number a multiple of 3? And so the same idea for the proof applies, but in this case we take everything mod 3. And so 10 is congruent to 1 mod 3, because 10 minus 1 is 9, which is a multiple of 3. And so by exactly the same logic, we can just sum the digits mod 3. So 1, 2, 3, 4, 5, 6 is congruent mod 3 to 1 plus 2 plus 3 plus 4 plus 5 plus 6. And then we can use the addition law to reduce these numbers mod 3. So 4 is 1, 5 is 2, and 6 is 3. I should have also reduced the 3's. But anyway, so 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 is 6, so it's 2 times 6. And 6 is a multiple of 3, so it's 2 times 0, which is 0, mod 3. What I could have also done is, that's 0 mod 3, and that's 0 mod 3. And we have 1 plus 2, which is 3, and 1 plus 2, which is 3. So anyway, that's congruent mod 3 to 0 plus 0, which is 0. There are lots of ways you can do these things. Or another thing, we could have just added them all up. So 1 plus 2 plus 3 plus 4 plus 5 plus 6, it's 21. And 21 is 2 plus 1 mod 3 by the same theorem. And then 2 plus 1 is 3, and 3 is 0 mod 3. Yeah, so these are some special things about digits and 3's and 9's. There's another one I'm sure you're familiar with, which is that a natural number is even if its last digit in base 10 is even. So if the last digit is 0, 2, 4, 6, or 8. So like before, we can write our number in some base 10 representation, and we observe that 2 divides 10 because it's 2 times 5. So 10 is congruent to 0 mod 2. And similarly, by a little induction argument, we know that 10 to the n is congruent to 0. Oh, wait, I made a little mistake there. I meant for all n where, for all n, if n is greater than 0, then that's true, right? Because 10 to the 0 is 1. By an induction argument, 10 to the 0 is also going to be 0 mod 2. Because, oh no, we don't even need induction. This is easy here. So 10 to the n, when n is positive, is 10 to the n minus 1 times 10, which is congruent mod 2 to 10 to the n minus 1 times 0, which is 0. So 10 to the n is congruent mod 2 to 0. Okay, so we can take our base 10 representation of our number and reduce it mod 2. So, or find what it's a congruent to mod 2. So n is congruent mod 2 to replacing all the higher powers of 10 with 0, but then but keeping the unit the same. And then that is certainly a 0. And so the conclusion is that n is even, which is to say that n is congruent to 0 mod 2, if and only if the last digit, the unit digit, is congruent to 0 mod 2. Okay, so that's kind of cool that we can rigorously prove that in sort of a quick way using these congruence manipulations. Recall back to the first lecture where we talked about this coin problem, which was whether it was possible to have 100 coins consisting of pennies, dimes, and quarters, such that the total value of all the coins that we have is $5. And what we did was we immediately turned it into a system of linear diophantine equations, which we didn't call it that back then, but given the previous lecture, that's what we can now call it. And so C plus D plus Q, so cents or pennies plus dimes plus quarters is 100, and then the value pennies plus 10 dimes plus 25 quarters is 500 cents. And let's say that we did have a solution. If we did, then we could take these equations mod 3. And so a couple observations, well, 4. 100 mod 3, well, the remainder after division, so 100 mod 3 is 1, because 3 times 33 is 99, and we have 1 remaining. And then 10 mod 3 is 1, and 25 mod 3, well, we can use our theorem just for fun, so that would be 2 plus 5 mod 3, adding the digits together, which is 7, and 7 mod 3 is 1. And then 500 mod 3, let's use the theorem again. It's 5 plus 0 plus 0 mod 3, and 5 mod 3 is 2. Okay, so reducing everything in sight, because these are just expressions involving addition and multiplication, we're allowed to do that. We get that C plus D plus Q is 1 mod 3, and C plus D plus Q is 2 mod 3. And so, by the transitivity and symmetry laws, we have that 1 is congruent mod 3 to C plus D plus Q, which is equal to C plus D plus Q, which is congruent to 2. So hence we would need that 1 to be 2 mod 3. So now there are a couple things that we can do to close off the argument. One is that since 1 and 2 are both residues mod 3, so they're in the range, they're greater than or equal to 0, and they're less than 3, then they have to, then because they're not equal, then that means that they can't be congruent. So that's one way to close it off. The other is to use the congruence definition directly. And so we can just see that 3 does not divide 2 minus 1, because 3 doesn't divide 1. So yeah, so that's a way that we can conceptualize why it is that this system was not solvable, because it's not solvable modulo 3. Every linear diophantine system of equations has to be solvable modulo every number. So if it's not solvable for one of them, then it's not solvable at all. Here's another thing we can do, and that's manipulate these horrible looking expressions involving the modulo operator. So if we take the remainder after division of a by n, and take the remainder of b divided by n and multiply them, and then take the remainder, then we could have just multiplied the numbers and taken the remainder. So let's see why. And we can just do this with congruence, which is great. So, okay, so we take the left-hand side, and because of that lemma, which was that congruence mod n, we can also just mod a number by n. That means that a mod n times b mod n is congruent mod n to the left-hand side, where we also take the remainder after dividing by n. And then similarly, a mod n is congruent to a mod n. So by using the multiplication law for congruence, then we can replace this expression with just a times b to get something that's congruent. And then, using just that same sort of theorem again, we can then take a times b and take the remainder after dividing by n to get something else that's congruent. And then because, by definition of remainder, that these are lying between 0 inclusive and n exclusive, they're both residues, and they're congruent residues, and so they are just equal. And then that is the statement. So there's one thing that we're going to study more in some future lectures is quadratic residues, which was a subject that Gauss was very interested in, and something called quadratic reciprocity for how do you predict which numbers are quadratic residues. So a quadratic residue is a residue of a square. That's it. So you take a squared mod n, and you see which numbers you can get. So let's look at a few examples for different prime moduli. So let's see, n equals 2. Let's make a table for all values of n that matter. So every number is congruent to either 0 or 1, modulo 2. And then a squared, like 0 squared is 0, 1 squared is 1. And then, well, those are already remainders after division by 2. So there's not very much going on with this table. So we've got our clock, and the green circles are representing which numbers are quadratic residues. So all of them are in this case. N equals 3. So we got 0, 1, and 2 being the 3 possible residues of a given number, modulo 3. And then we square them. So we get 0, 1, and 4. And then we take the remainder after division by 3, and we get 0, 1, and 1. So 2 is not a quadratic residue, and every other number is mod 3. Let's look at 5. So now it's 0, 1, 2, 3, or 4, being the 4 residues mod 5. We square them all and get 0, 1, 4, 9, and 16. And then we take the remainders after division by 5 to get 0, 1, 4, 4, and 1. So the only quadratic residues are 0, 1, and 4. So we see those are the ones with the green circles, and 2 and 3 are not residues. And then 7 it's like the same thing. So we now go through 6 squared, and we take it mod 7, but the only residues are 0, 1, 2, and 4, and 3, 5, and 6 are not. So one interesting thing is that if you exclude 0 and also exclude the n equals 2 case, then exactly half the numbers are residues and half are non-residues. So for 3, we've got 1 residue, 1 non-residue, quadratic residue, quadratic non-residue. And then for 5, excluding 0, we've got 2 quadratic residues and 2 quadratic non-residues. And then for 7, we got 3 quadratic residues and 3 quadratic non-residues, again excluding 0. Yeah, and so it's kind of a random seeming pattern, and one goal will be to try to figure out which ones are residues and which ones are not. So I guess one little pattern to notice is that, so like why is it that 2 and 5 are the same number squared? Well, that's because, well, one thing we know just from basic algebra is that minus a squared is a squared. But another thing is that minus a is congruent to n minus a mod n, because n is congruent to 0. So a squared is so a squared is then congruent to n minus a squared, for example. So there's the symmetry that we always see. So that's one little piece of the pattern. Now let's look at a neat application of modular arithmetic, which it's not strictly necessary to use modular arithmetic for this, but it's a good experience for us to go through and try it. And that is to show that the square root of 2 is irrational, so it's not equal to any ratio. Starting off like the usual proof, which you might have seen before, we suppose for sake of contradiction that the square root of 2 is in fact equal to a ratio. And we'll say that a and b are both natural numbers. B has to be bigger than 0. Of course, we can't divide by 0. And neither are negative, just because if this is a positive number. So one thing that we can assume to simplify this, and also this is the lever against we'll push to crack open the logic to show that this is a contradictory case, and that is that the GCD of A and B is 1. And the reason that we can assume this is that if the GCD weren't 1, then we could divide the top and the bottom by the GCD to get two numbers that are coprime. And it's an equivalent fraction. Yeah, so we reduce the fraction and we assume that the numerator and denominator are coprime. Okay, let's rewrite this as a diophantine equation. So first of all, squaring both sides, we have that 2 equals a squared over b squared. And then multiplying by b squared, we get that 2b squared equals a squared. And so what we are actually trying to show is that this diophantine equation has no solutions. And because this is equivalent to square root of 2 being irrational. Okay, so this is our equation. And so one thing we can do is consider it modulo 2. So 2b squared modulo 2 is 0, because 2 is congruent to 0 mod 2. And then by our analysis of quadratic residues, so let's look at our table again. So when x is 0, then 0 squared mod 2 is 0. And when x is 1, 1 squared mod 2 is 1. So mod 2, we can just erase squares. So a squared is just congruent to itself, mod 2. And so then by joining up all these, by using symmetry and transitivity, then we see that a is congruent mod 2 to a squared, which is equal to 2b squared, which is congruent to 0. So a is congruent to 0 mod 2. That is what we see through this. And so a is an even number. We didn't need to do this mod 2, just to be clear. We could have said, well, 2 divides a squared. 2 is prime, so it has to divide a or a, because a squared is a times a, so 2 divides a. But this is a neat little use of modular arithmetic. So now let's look at it mod 4. So let's look at a table of all the squares mod 4. So we have 0, 1, 2, and 3, which we square, which we then take the remainder. So 0 squared is 0 mod 4, 1 squared is 1 mod 4, 2 squared is 0 mod 4, and 3 squared is 1 mod 4. So since a is even, a is one of these two cases. It's either 0 mod 4 or 2 mod 4. And since a is since it's one of those, when we square it, we see we get either 0 or 0. So a squared is 0 mod 4, just by looking at this table. And then also, since we know that 2b squared equals a squared, that means that 2b squared is congruent to 0 mod 4, just by substituting things mod 4. So then we can look at the table again and think, okay, which values of b, when we square them and multiply them by 2, give us 0? So we can just go through. So 0 squared times 2, that's 0. Okay, so that's a possibility. 1 squared times 2 is 2. So that's not 0, mod 4. So that's not a possibility. 2 squared times 2, mod 4. Yeah, that's 0. So that's in our list. And 3 squared times 2, mod 4, that's 2. So that's not a possibility. So the only options are b is 0 or 2 mod 4. And since that's the case, then one thing we can see is that b is even. And I skipped a little detail here, which was if it's one of these, then it's even, but that's a little exercise to you. Okay, so through this analysis of mod 2 and mod 4, what we have is that a is even and b is even. So in other words, 2 divides a and 2 divides b. But that's a number that divides both of them, so it has to divide their GCD. But that contradicts the fact that their GCD is 1. So that means that this was all impossible, and so therefore, in fact, the square root of 2 is not equal to a ratio. Okay, so the square root of 2 is irrational through these analysis of diophantine equations. As a last example, let's look at n choose k and just sort of explore evenness versus oddness of it. So, and this also is related to what was on the homework, which was looking at different properties of, or at least just seeing that was an integer at all. So, okay, so n choose 0, that's just always 1, and that's something you can calculate. And n choose n, that's 1, which is what you can calculate. So both of those are always odd. And on the homework, you showed, just using some algebra, that n plus 1 choose k plus 1 is n choose k plus n choose k plus 1. So anyway, we can take that equation mod 2. So let's just write a little table for what that looks like. So addition mod 2 has this table. So 0, let's see, the only interesting one, I guess, is that 1 plus 1 is 2, which is 0 mod 2. So that's the mod 2 addition. So one thing that we can do is we're going to create a table of which of these numbers are odd. So, so for example, if there's, so n will be the rows, k will be the columns, and then this formula that we have says that to calculate it at the n plus 1 k plus 1 position, we have to go up a row, see what's there, and then also go up a row and go to the left one and see what's there, add them together, mod 2, and that will tell us the evenness or oddness. So let's see. We have a base case, which is 0 choose 0 is 1. And also n choose whatever. Let's see, n choose 0 is always 1. So those are all odd. Also, so now we use this rule. So like the 1, 1 entry. So we look at the 2 entries right above it and to the left, and there's exactly 1 that's odd between them. So this is odd. Okay, so now the 2 choose 1. We look at the 2 entries above it in that pattern. Odd plus odd is even, so there's no dot there. The 2 choose 2. Well, we look up, there's odd and even, so odd. Odd plus even is odd. So now the 3, 1 entry, that would be odd plus even, which is odd. The 3 choose 2 entry, that would be even plus odd is odd. And then again, odd plus even, odd. Now this one would be odd plus odd is even, odd plus odd is even, odd plus odd is even, odd plus even is odd. Okay, I'm not going to fill this all out live for you, or at least recorded for you. Let's look at what it actually ends up looking like. And so then we get this intricate pattern of all these triangles nested all together. And you may recognize this as being a Sierpiński triangle-like shape. So that's remarkable. What's the Sierpiński triangle doing in number theory? And maybe we'll learn some reason why later. But, maybe this at least piques my curiosity. Okay, so let's summarize what we talked about in this video. So we introduced congruence modulo n, which is this equivalence relation that respects addition, subtraction, multiplication, and also raising to fixed powers, as we saw in a few examples. And it makes reasoning about divisibility much easier than it otherwise would be, because it makes it so that you can just throw away different multiples of a given number just immediately. Because without modulo, you have to always be keeping track of that multiple of n in all of your expressions. And anyway, why do that? Well, I hope you enjoyed this topic, and I hope you enjoyed the examples, and I will see you next time.